So before that, let's have a brief discussion which is very much required to remember all the time while studying this subject. Electromagnetic fields is combination of two parts. One is electrostatic and another one is magnetostatics. So we are talking about electrostatic. In electrostatic, we have to consider the terms related with electric field. There are two terms related with electrostatics. One is capital E, which is electric field intensity, and another one is capital D, which is electric flux density. So today we are going to discuss about electric field intensity. It is also called as electric field strength. So we deal with voltages and currents in circuit theory. In circuit theory, we study electronic devices, pulse and digital circuits, or any other analog related subjects. There all the signals are dealt with voltage and current where we can directly apply Ohm's law. We may have signals in the form of alternating currents and voltages. Normally, we denote Vm for maximum voltage value, Im for maximum current value. Alternating current have a sinusoidal signal value. But in field theory, we don't consider voltage and current. First part of this unit is based on Coulomb's law, and Coulomb's law is based on Newton's law of motion. So let us discuss how it is derived from Newton's law. This law of this unit is called as Coulomb's law, which is based on Newton's law. Newton stated that if two masses are separated by some distance r, then the force between these two masses will be given by product of two masses, and it will be inversely proportional to the square distance between them. On the same lines, Coulomb's law of two charges is made. We can consider charges as a single point, like we have shown here. A single point, a single dot is nothing but a charge. A single charge can be represented by a single dot. For understanding purpose, if we zoom out this small point charge, its shape will look like a sphere. So throughout our discussion, we will consider a charge in a bigger view. These charges are placed in space. They have their fixed position. We have discussed in the Cartesian, cylindrical and spherical coordinate system that charges are placed in 3D atmosphere, and we have to consider their position in space. We can have charges at various positions and various situations, and there are other charges also present in the space which may be applying forces on each other. There may be different kind of forces. Normally we consider like force of attraction or force of repulsion. So if we consider two charges and give them name as q1 and q2, and if they are separated by a distance r, then force between them is given by Coulomb's law. As the distance increases between the charges, the obvious observation we can make is that the force will decrease. If you apart from your friend, as distance increases, then the force between you and your friend of attraction may also reduce with the time. Now, what is electric field intensity? What we have discussed so far is about force, which is given by Coulomb's law. The formula for Coulomb's law force is given by F, which is directly proportional to the product of charges, say charge q1 and charge q2, and they are inversely proportional with the distance r square. When we write equal to, we have to consider constant of proportionality. which is given by 1 upon 4 pi epsilon naught. In previous session we have seen about it and we also discussed the examples. So this is formula for force. When we write it like this, it is a formula as a scalar. If we want to consider as a vector, we have to give one bar on the head of F. And then we can add a directional component. In general, we will give it as A R cap. So there is a direction in the space. So this is full formula for Coulomb's law in vector form. What is electric field intensity? Electric field intensity is defined as this force per charge. How much force we are applying on a particular charge. Suppose we have two charges. Say this is charge Q1 and here the small one is say charge Q2. Now if I want to calculate how much this small charge is applying force on this Q1, then I can find out that force by using this formula. But if I want to calculate what is the electric field intensity applied by this point to this point, that is from Q2 to Q1, then the formula is force per charge. So if we consider this formula and if we want to modify it for electric field intensity, then we have to take it force per charge. So if we want to calculate force per charge Q2, how much on Q2, then we have to add one more Q2 at this RHS. So for this formula of electric field intensity, which is force per charge, in force formula we are writing this Q1, we want to calculate force per Q2. Then this Q2 will get cancelled. So what will be the remaining formula for electric field intensity? So electric field intensity E can be given by E bar, it will make it vector, it will be equal to, now we have only one Q remaining at the numerator. So it will be Q divided by 4 pi epsilon naught R square. So this is 4 pi epsilon naught R square, and we have to take direction component as it is a vector. So this is A, consider it as A, so this is AR cap. Okay, so you just consider it as air cap. I could not write it properly. So the point is electric field intensity is force per charge. So right now we have a formula which we have derived from Coulomb's law of force, and this is our first expression for electric field intensity due to point charge on another charge. So if we have a single charge, then this formula will be applicable. If we have more number of charges, it will be considered as charge density. So that also we will discuss. So here we can see the formula for force. For force, we have two parts here. One is magnitude and another one is the direction. So from this force formula, we have just seen how to derive electric field intensity. Now what is a charge? If we go closer to the charge, what is behavior of this charge? If it is a positive charge, every charge emits some force lines. And how we are defining electric field intensity? We are defining it as the force per charge. That means there are some force lines coming out of this particular charge. So these charges are emitting force lines. These emitting force lines are nothing but electric field intensity, we can say. So here we are using electric field intensity which is coming out of the basic element, which is charge. So if this is my charge Q and it is positive, then the force lines will come out from this positive charge, and these lines will always perpendicular to the surface of charge. You can consider it as a sun. When we have sun emits energy in all direction. As the rays go away from the sun, all the lines looks like parallel to each other, because as distance increases from the sun, the distance between two rays also increases. So the distance between two rays which is near to sun is smaller, but as they go away, their distance increases. So for a viewer, they looks like parallel. So what we have to remember here, if positive charge is there, electric field intensity lines will go out, and electric field intensity lines are always perpendicular. If it is a negative charge, opposite will happen. That means electric force lines will come inward to the negative charge. So that is the reason, if there are two like charges, positive Q, and all of them are giving out force line. So this one is giving out force line, this Q is giving out force line, and these both opposite side force lines are repelling each other. But in case of opposite charges, positive Q is sending out the force line, and negative Q is taking inward the force line. So they are attracting each other. Now same thing we have to consider here. In classroom, if we have a source point and there will be various destination points, and there will be application of force from source to destination. That if someone is trying to teach, he is applying some force, and if someone is trying to understand, he is receiving the force. So we have to consider the destination and source. So normally in mobile communication, we consider as a mobile tower is a source who is applying electric field intensity outside. There will be combination of electric and magnetic field intensity, but here we are considering the electric field intensity of a wave. So we may have charges at various position in space. Few may be positive, few may be negative. So if there is a positive charge will emit outside the force line, and for Q it is coming inside. If there is another positive Q, is sending out the lines, and this one is receiving inward inward movement of force line. So electric field lines are coming towards negative charge, and they go away from the positive Q. And at the surface level, electric field intensity lines are always perpendicular to the source. If it is a source, the basic element of any source is charge. Now what is the direction of electric field intensity? For understanding the direction of electric field intensity, we can consider this example where we have a capacitor and a inductor. So all of us know that capacitor is used for storing energy. So if we consider this capacitor, so capacitor will have two plates, one will be positive, another one will be negative. So always we have to remember that electric field intensity will always travel from positive to negative. So if it is a positive plate, it will go from start at positive plate and it will go at negative plate. If it is a resistor, it will also travel from positive to negative. If it is a voltage source, in voltage source also we will have one positive terminal, one negative terminal. So this direction of electric field intensity will also travel from positive to negative. Let us focus only on transistor in our attached slide. Say this is a view of capacitor. Here we are showing virtual electric field lines. So here these are the electric field lines. So these lines, these arrows we are representing as electric field intensity. All of them are electric field intensity lines traveling from positive to negative. We don't see that there are direct arrows, we are just representing that field, electric field intensity lines are traveling from positive to negative terminal. And then it will continue to the next part of circuit. It may be resistor or battery. Now, if we consider the density of charges, density is very important concept. So, when we deal with the wires or any other antenna, then there won't be only a single charge. There will be density of charges. Density means there will be more number of charges present at particular place. So, if we consider this surface, now how we get this surface? Now, if we imagine that this is a conductor. This is my conductor, there will be a wire of conductor. In conductors, we get the electrons as charges. If we zoom out the conductor shape, we will get a cylindrical shape of a wire. Now, where exactly these charges appear inside a wire? So, if there are electrons, because atoms are present in the inner material also. So, electrons which are easily available in conductors are available inside material also. But whenever there is a flow of current, the charges inside material vanishes and they appear on the surface. This time is called as relaxation time. In some other topic we will discuss it. And these charges, they disappear inside material and appear on the surface. And on surface they flow. And from this surface we get the lines of electric field intensity. Those are perpendicular to the surface. So for a conductor also, we will have the electric field intensity parallel to that particular conductor. So what we have to remember here, inside conductor value of Q, that is charge, will be 0. Inside conductor, if Q is 0, electric field intensity is also 0. Charges flow on surface and electric field intensity also is perpendicular to the surface.